In the name of Almighty God, I'm Asas and Kushan. Today I want to talk about these thermal X-rays breaking out from pre-explosion ejecta of dying massive stars. I read it until the fifth page. As a baseline test, we fetched the multi-band light curves of SN2026J ZF with a purely radioactive model powered by the decay chain of nickel 56 using transfeed, a time-dependent radiative diffusion code for supernova light curve interference. The best fit model shown in figure 4 requires a nickel 56 mass of 0.45 m and an ejecta mass of 1.85 m to reproduce the shallow rise, and it's about 10 days peak with radioactive heating alone. The model further requires nearly complete nickel 56 mixing with X nickel is equal to 0.993, which corresponds to an almost homogeneous distribution of radioactive material throughout the ejecta. Such a strong mixing could, in principle, be enhanced by explosion-driven hydrodynamic instabilities in a compact Wolf-Rayet progenitor that experienced vigorous late-stage mass loss. However, this level of nickel-56 homogenization is difficult to obtain in multi-dimensional explosion simulations, which generally produce asymmetric, clumpy, or finger-like distributions of iron group material rather than a nearly uniform radioactive component. If weaker mixing is imposed, the early emission can be reproduced only by reducing the ejecta mass to below about 1 m, which is unusually low for a strip enveloped supernova. The relativity high nickel to ejecta mass ratio is greater than 25%, suggests that other energy sources may play an important role in powering SN2026 GZF methods. It should be noted that the data at less than 10 to the power of 4 are significantly higher than the prediction of the supernova model if taking into account the initial cooling of the supernova ejected, a large radius, and higher temperature infrared from these early optical booms indicates that the boom strays and emission region beyond the supernova eject and expand at a velocity of almost 0.7 c meters. This may point a super relativistic cocoon driven by a relativistic jet. However, as noted previously, any jet involved here would be chucked deeply inside the progenitor star, consistent with the non-detection of gamma rays. Accordingly, a hot super relativistic cocoon is the sole observable outcome of the jet and produces the observed early optical boom. This further demonstrates the importance of timely detection of supernova from the SPO emission. Finally, from the single detection of EP 260-321A in the systematic survey with the EPWXT, we derive a local event rate density of X-ray SPO transit of rho 0 SPO EP260321A is greater than or equal to 170 GPC to the power of minus 3 Y R to the power of minus 1 above a peak luminosity of 1 multiplied by 10 to the power of 45 ERG S to the power of minus 1. This, this event rate density sits between the more common XRO 0.80109 associated with an SNIBC and the more luminous and rare event XRF 0.60218 associated with an SNLICBL, forming a power law luminosity function for X-ray detected SPOs with an index of 1.3 plus positive negative 0.4 as shown in the right panel of figure 3. This fact, together with more common SPOs observed in the optical band in type 2S and E, implies a unified scheme for stellar shock breakouts, with rarer, more luminous events rising from more extreme stellar explosions involving higher angular momentum and more envelope stripping. Furthermore, the detection of supernova SPOs yields more precise timing of core collapse events compared to optical supernova. This allows for more efficient searches for associated neutrons and potential gravitational wave signals in the nearby universe. Further continued observations with Einstein probe and other wide field monitors, together with simultaneous multi-messengers observations in gravitational waves and neutrons at the time of SPOs, will further constrain SPO physics and may uncover how massive stars and their lives. Figure 1 illustrates X-ray optical images and X-ray evolution of EP26O321A upper WXT and FXT image in zero point 0.4 to the 2 kilo electron volt. The white circle shows the positional error circle of WXT with a radius of 2.70, 90% confidence level. The optical image is the composite Mephisto gray band image taken as the T0 plus 2.3 hours lower. The evolution of unabsorbed X-ray flux in the zero point 0.4 up to 2 kilo electron volt upper and temperature lower under the absorbed blackbody model. The transit began at T0 is equal to 2026 March 21, corresponding to the time of the 3 sigma excess above the background. Raw count rates were converted to the unabsorbed flux using the factors determined by the time result spectral fitting methods. The vertical errors bars show the 1 sigma uncertainty, and the horizontal error bars indicate the corresponding time intervals. The solid lines represents the best fit with a supernova SPO model methods. Figure 2 illustrates X-ray spectra of EP 26 221. The WXT spectrum includes data from T0 to T0 plus 2200. The FXC spectra include data from T0 plus 1065 to T0 plus 2359 second. The count rate of the FXCB spectrum is significantly lower than that of FXC, since the counts in the core of the point spread function of fxtb were excluded in the spectra to mitigate pile-up effect. Metals the data points are shown with 1 sigma uncertainty, and the lines represents the best fit absorbed blackbody left and power law right models. So figure 4 illustrates multiband optical and near-infrared evolution of SN 2026. Apparent magnitudes are plotted as a function of time, with vertical offset applied to individual filters for clarity. Open downward triangles mark upper limits. The solid lines give a theoretical fit of the light curves by invoking power due to the radioactive decay of nickel 56, with the shaded bands representing the 1 sigma model uncertainty. The methods we want to talk about it: Einstein probe observations and data reduction. Einstein probe 260 triggered with the wide field X-ray telescope WXT onboard processing unit at 2026. The March 21 at time is 12:30 based on the UTC time during its survey observations with a signal to noise ratio or SNR of 7. This source was also detected in the preceding survey observation and the autonomous follow up observation. Thus, WXT observations covered the entire onset and decay phase of this transit with the local exposure time of about 3,100. The X-ray events were processed and calibrated using the dedicated data reduction software and calibration database developed for the WX instrument. The CalDB, or exactly the calibration database, was constructed based on the results of ground calibration experiments following procedures previously applied to a WXT prototype. Photon positions were transformed into celestial coordinates in the J2000 reference frame. The energy of each event was determined using the basis and gain parameters provided in the calibration database. After identifying and flagging bad and flaring pixel, single, double, triple, and quadruple pixel events without anonymous flags were retained to produce the clean event files. The zero point 0.4 up to 2 kilo-electron-volt image was generated from the clean event list. Figure 1 source and background light curves, as well as time-resolved spectra, were extracted from SQL region with a radius of 9 print and an annular region with inner and outer radius of 18 print and 36 print respectively. The peak count rate in the source region was only 0.01 counts per frame, indicating that the pile-up effect in the WXT data was negligible. An autonomous follow-up observation was carried out with the follow of X-ray telescope FXT and lasted for 2 orbits with an exposure time of 4,267 seconds. The FXTA and FXTB were working in the partial window and full frame modes respectively. The level 1 image files were processing using the FXT data analysis from V1.30 together with the corresponding calibration database V1.30. The reduction procedure, including particle event identification, pulse invariance conversion, grade assignment, and selection, grade is less or equal to 12, flagging of bad and hot pixel, and the screening of good time intervals based on the housekeeping data. This pipeline produce cleanup event files for FXTA, source and background light curves, as well as time-resolved spectra were extracted from circular region with a radius of 1 plane and from two adjacent circular regions, each with a radius of 30 degrees respectively. For FXTB, the source region was an annuals with inner and outer radius of 20 zegon and 1 brane. To mitigate a pile-up in the full frame mode, the corresponding responsible files were then generated with the point spring function corrections. In addition to autonomous follow-up observation, FXT conducted 6 observations to monitor the long-term X-ray behavior of Einstein probe 26 0321A extended data table. No significant detection was found in this observation. X-ray spectral analysis. Since there is no significant signal above 2 kilo-electron volts, the X-ray spectral analysis was performed over zero point 0.4 up to 2 kilo-electron volt and zero point 0.3 up to 2 kilo-electron volt for WXT and FXT and X-spec respectively. The spectra of FXT A and FXT-B were generated separately and fitted simultaneously. The W statistics was employed in deriving the best fit spectral parameters. The integrated and time-resolved spectra were rebinded to at least 10 2 and 3 counts per pin, respectively. The integrated spectra of the WXT T0 T0 plus 2200 second and FXT T0 plus 1065 second, T0 plus 2359 second, and for example, the first orbit of the autonomous follow-up observations can be well described by an absorbed blackbody model, where the first and second components respectively account for the galactic absorption NH and galactic and the intrinsic absorption NH, and the third component is the blackbody function in the source rest frame, the column density of the galactic absorption in the direction of the Einstein probe 260 321 was fixed at 2.64 multiplied by 10 to the power of 20 1 per square centimeter based on the reference 15, and the redshift was fixed at 0.0344. If the NH of the FXT is linked with that of WXT, the best fit parameters are NH is equal to 8.4 minus 1.5 plus 1.6 multiplied by 10 to the power of 21 per square centimeter. Ka temperature absolute is equal to 124 minus 6 positive 7 electron volt, that based on the WXT telescope, and 112.7 between the minus 2.1 top to plus 2.1 electron volt FXT with an acceptable statistics W stat DOF or degree of freedom is equal to 245 point 7 divided by 231. The goodness of fit is not significantly improved with the independent NH. If the integrated spectra was fitted by an absorbed power law model, the goodness of fit is much poorer with a statistic of W stat degree of freedom is equal to 272.2 divided by 231, and the best fit photon index is about 10, is also on physical right panel on figure 2. The difference of the Bayesian information criterion delta B is equal to 26.5 indicates strong evidence against the absorbed power law model. A cutoff power law could fit in the integrated spectra acceptably with a cutoff energy of about 120 electron volt and photon index of about -2, which effectively mimics a blackbody function. To investigate the possible spectral evolution, the WXT observation was divided into four segments. The FXT observation during the first orbit of the autonomous Phala observation was divided into six segments of each FXT module, 12 FXT segments in total. The resulting 16 spectra were simultaneously fitted by an absorbed blackbody model. The NH values of all segments were linked, assuming no significant variation of the intrinsic absorption. The blackbody temperatures of FXTA and FXTB in the same segment were also linked to spectra of all segments are consistent with the absorbed blackbody model. The best fit NH is 7.9, the threshold minus 1.6 to positive 1.7 multiplied by 10 to the power of 21 per square centimeter. The blackbody temperature slightly decreased from 135 electron volts to 110 electron volts. Extend the table to extend the data figure 5. In the second orbit of the autonomous Phala observation, T0 plus 5,137 says, T0 plus 8,111 seconds. Based on them, Einstein probe 260 was still well detected with a significance of about 5. The flux was estimated to be 7.5, 1 plus positive negative 2.5 multiplied by 10 to the power of minus 14. ERG1 divided by square centimeter and a second in the zero point 0.4 up to 2 kilo electron volt by assuming an absorbed blackbody with NH is equal to 8 multiplied by 10 to the power of 21 per square centimeter, and KT absolute is equal to 100 electron volt. Additionally, the 3 sigma upper limits for the non-detection in the other FXC observations were derived under the same spectral shape. Extended table 1. Figure 5 illustrates the evolution of the time-resolved WXC and FXC spectra. The data points are shown with 1 sigma uncertainty, and the lines represents the best fit absorbed black-body model. The data points of WXC and FXC spectra are rebind to 2 sigma and 3 sigma significance respectively for clarity. The numbers in the square brackets of the legend represents the time intervals in seconds relative to 20 is equal to 2026 then March 21 at the time 12:16. Based on the UTC time, the best fit spectral parameters are shown in the extended table 2. Now I want to go through another method, which is optical and near-infrared photometric observation. Our ground-based optical and near-infrared photometric observations were conducted using multiple facilities and are still ongoing. The current results are summarized in extended table 3. The 1.6 meter Mephisto telescope began imaging the field 36 minutes after T0 operating simultaneously in either the UGI or NURZ band. The Jinshan project commented continuous monitoring in the degrees J bands using the 1 meter 100 R and 100 B and 100 C and zero point 0.5 meter 50 ampere telescopes starting at T0 plus 1.8 hour. The 0.76 meter Cosma automatic imaging telescope observed the field in the BVRI and clear bands from the T0 plus 16.5 hours. Further optical observations were carried out with the 2.5 m wide field survey telescope WFST in the UGR bands starting at T0 plus 2.04 days. Additional photometric data were obtained with the Tsinghua NOC 0.8 meter telescope TNT. The 0.7 m telescope of the Thai Robotic Telescope Network located at the Springbrook Remote Observatory or SPO, and the Cerro Tololo Inter-American Observatory CTO. SORAS 1 meter Zeiss 1000 optical telescope Zeiss 1000 and 0.5 m AS 500 divided by 2 telescope, the 2.56 meter Nordic optical telescope NOT, the 2.6 meter Shahjan telescope, and the 50 centimeter Maksutov telescope of the Crimean Astrophysical Observatory, and the 1.5 meter AZT-33 telescope of the Mandi Observatory along the line of the site of the Einstein probe to 26021 SN26JZDF galactic extinction is B minus V is equal to 0.021 Mach. All photometric images were calibrated following standard procedures including bias subtraction, dark current subtraction for CMOS detectors, and flat field correction. We used astrometry.net and SCAN for astrometric metric calibration (RRIF) and SWARP for image stacking. Aperture photometry on the reduced image was carried out with the Sextractor Mephisto UV GRIZ. Photometry was calibrated against the kinetic photometry derived from the recalibrated Gaia spectra. The Solon Greece, as well as J-prime, R-prime, I-prime, Z-prime photometry was calibrated against nearby reference stars from the Pan-STARRS DR2 catalog in the AB magnitude systems. For the Johnson-Cousins filters, the BVR-CLC band photometry in the Vega system was calibrated using magnitude converted from the Solion system. To subtract the host contribution, we use hot pans to perform image subtraction. Template image were used multi-band stack images from the pan star star RS PS1 survey unfiltered coded images from the Catalina Sky Survey, BB band archival images from the Los Cumbres Observatory or LCO network, and a J band archival image from the UKRIT Infrared Deep Sky Survey. Images from the Mephisto and WFSC were subtracted using their own archival templates. Photo Tiles was then used to perform aperture photometry on different images to obtain the transit magnitude. Optical spectroscopic observations to investigate the ejecta properties and chemical evolution of SN2026 GZDF, we conducted a multi-epoch spectroscopic campaign spanning from T0 plus 2.7 days to T0 plus 56.4 days. In 19 high-quality spectra were obtained which their detailed observational parameters listed in the extended table 4. The resulting spectral sequence is illustrated in the left panel of extended data figure 6, providing a comprehensive view of the transient's spectral transformation. All spectroscopic data were reduced using standard procedures within IRAF, including biosubtraction, flat filling, and optical extraction. Wavelength and flux calibrations were performed using daily helium-nickel comparison lamp exposures and spectrophotometric standard stars respectively. Low resolution optical spectra were acquired using the ALFOSC spectrograph on the 2.56-meter Nordic Optical Telescope or NOT between 2026 March 26 and May 16. 13 reliable spectra were obtained by the following procedures. They employed Greece, the number 4, in the conjunction with a 1.3 Zegon real link. A typical spectral resolution of R is equal to lambda divided by delta lambda is equal to 300, and a usable wavelength coverage of 3800 to 9200. We perform multiple successive exposures at each epoch, allowing for a robust removal of cosmic rays during the image stacking processes. The spectroscopic data were reduced using standard IRAF-based pipelines, including bias subtraction, flat field correction, and one-dimensional spectral extraction. Wavelength calibration was anchored to helium-nickel comparison lamp spectra. Full calibration was achieved using the spectrophotometric standard stars, for example, FIG 34 or HD 84937, observed during the same nights at similar air masses with their reference spectra taken from the Oak catalog. Follow-up spectroscopy was also conducted using the CASS double spectrograph mounted on the 3 AM Shane telescope and Lick Observatory. Three of the spectra were acquired between 2026 March 24th and 2026 March 27th. The observations utilize a dual beam configuration with the D55 dichroic mirror, typically employing a 6000 per 4310 grating for the blue channel and a 300 per 7500 grating for the red channel. This setup provides a broad and continuous wavelength coverage from the almost 3500 to 10500. So welcome to the uh, sun star dying. The line to the wide slit was aligned at the parallel angle Filipenko 1982 to minimize differential light losses caused by atmospheric dispersion. A complete log of the CAS observations, including explosion times and specific instrumental stop for each epoch, is detailed in extended table 4. So there is a specific car is with a loud music. It's booming, booming, booming. While I'm reading their articles, they are happy. I don't know why, because I'm reading some things. They are very happy. Additional optical spectra were obtained using the BFOSC instrument mounted on the Zinc Line 2.16-meter telescope of the National Astronomical Observation. Chinese Academy of Science and NOAC. The observations were carried out between 2026 March 26 and April 15. So I'm not very. I have no emotion towards them. They are just passing through a street. This street, every single body has this address. So I just want to declare that I also have some sort of emotion, some sort of balance, panel and plan, a really plan panel to do something, and I am very happy that. I have many enemies. Yielding to high quality spectra, we utilize the GRISM for G4, which combined with a 2.3 second slit provided wavelength coverage of 3,609,000. A detailed journal of the BFOSC observations included in extended table 4. No, there is no time to stop them. So let's, whatever madness you want to extrovert your madness here. I'm capturing your madness that you are passing through my streets, and I'm capturing it, and finally eventually it's recorded in my laptop. It's etched in the university. So don't think that you are invisible to this universe, as you have some sort of toys that you call it as a satellites or telescope. There is something very big with a high technology. You have no understanding about it. Never you will have it, and it's very fantastic. So whatever you did toward me, it is etched to the university. No reversal point. Absolutely, it is irreversible. Whatever you did to me, it is etched to the university. So extrovert your emotion in a street, and whatever you want to have an enemy and aggressive towards me, show it. You can comment, you can curse me, whatever you want to do, but just now that I have blocked everything. So this is because of these aggressive people around me, and doesn't matter where I go. I went to Norway, I saw it. I went to Germany, I saw. I'm living in New York, I saw it. So it doesn't matter if I change. I reached to the conclusion that I totally must change something fundamentally. It's not by changing my country you can make it true correct. So for tonight, I think that is enough to know that how sun can be exploded. If there is any simulations that I can do it for you, you can download it from github.com/masterscript, github.com/cautionscript, github.com/safaroscript. Today is 23rd of June 2026. Time is 1:23. I didn't correct my region, so it's not correct. It's in another region.